back, and now we want to talk about the theory of elasticity. And the first concept is, what is a stress? So a stress is going to be a force applied to an area. Now you should already know what a force is. So a force is a push or a pull. So if you have a refrigerator and you're pushing on it, you're applying a force to it. If you are playing tug of war, you're pulling on a rope, so you're exerting a force on it. Now, a stress is slightly different because now we are specifying that the force is being applied to an area. So that, for example, if you have a sheet of paper that's like this and it has a certain area A, and then you apply a force to it like this, then you are applying a stress on that piece of paper. You could also apply the force at an angle. So sometimes the force is going to be perpendicular to the area, but sometimes the force can actually be at an angle to that area. An example of a stress might be like an ice skater. And so an ice skater, the blades on the ice skates have a certain area on them. So the bottom part of the blade of the ice skate has a certain area A, and then your weight pushing down on those ice skates, that's going to be the force. So you are going to be applying a stress to the ice whenever you are skating on it. Now let's look at the units here. So the stress is force divided by area. So its units are going to be newtons per meter squared. So that's going to be the official metric unit for stress. Now a strain, on the other hand, is going to be when you apply the stress to an object, how does the object respond to that stress? So let's pretend, for example, that you have a rod. So this could be a cylindrical rod. So this is the area of the top of the rod. And then you are going to pull on it. So you're going to be applying tension to that rod. So the direction of your force is going to be up and down on that. And now let's say that the original length of the rod was L0 for original length. So that's this distance from here to here. And now you're going to stretch it. So what's going to happen is it's now going to turn into something like this. So it's going to be all stretched out. So notice you have a different length. Now the area didn't change, but the length did. So maybe we want to call this L final. So for the final length of it. And therefore the change in the dimension is going to be L final minus L sub 0. So that's this distance right here. So that would be your change in dimension. And then the original dimension is going to be this thing right here. So notice that the change in dimension in this particular example would be meters, and then the change in the dimension would be in meters. So notice they cancel each other out. So strain does not have units to it. Stress does, but strain doesn't. So stress is what's causing the change. Strain is a measurement of the change. And then the ratio of stress to strain is going to be called the elastic modulus. It's a number, and it depends on the substance. So if you've got a rubber band and you hang a weight from it, it's going to stretch a certain distance. But if you've got a piece of metal and you hang the same weight from it, it's not going to stretch as much. because they're made of different materials. The atoms are hooked together in different ways, and so they're going to have different elastic moduli. So this would be something that you would look up in a textbook. So if we want to look at the units for elastic moduli, we know that stress is going to be newtons per meter squared, and we know that the unit for strain is nothing. So therefore, the unit for the elastic moduli is newtons per meter squared. It's exactly the same as it was for stress. Okay, on this next slide, I just wanted to show you the different kinds of stress. You've got tension when it's being pulled like this, so that the stress would be tension, and you can see in that picture there the L sub 0 and then the change in the length. You could have compression where you're pushing two things together, and this time it would produce a negative strain. So this time the change in length is going to be smaller, so it's going to be a negative strain. You could also have shear. So an example of shear would be, let's say you have a deck of cards, and then you push on the top of the deck of cards, and it makes the deck of cards lean over. So that would be shear example. So notice it's kind of like compression, in which you got two forces like this, but they're offset, so that it's like this with shear. And then you could also have torsion, and so that is where you've got a cylinder and you twist it, so you're applying a torque to it, and that's going to change the shape of that cylinder. So those are all examples of different kinds of stress and then the associated strain that goes with it. So here's a sample question. A force of 2 times 10 to the 6th newtons is applied to the end of a steel bar that has an area of 1 centimeter squared. How much stress is placed on the bar? So we're going to write down what we're given. We know that the force is 2 times 10 to the 6th. Now be careful with the area, because the area must be in meters squared, not centimeters squared. And then we're looking for the stress. Okay, now we're going to select our equation. So stress is force divided by area. Put the numbers in there, and we end up with 2 times 10 to the 10th newtons per meter squared. Now in part B, assume the bar in part A was originally 10 centimeters long, and it stretched 1 centimeter when the stress was applied to it. How much strain did it experience? So the original length is 10. The new length is going to be 1. The change is going to be 1. So what's the strain? So we're going to take 1 divided by 10, which is going to be 0.1. Now, somebody might be saying, oh, but shouldn't I have changed the length to meters? And shouldn't I have changed the change in length to meters? Yeah, go ahead. But what you're going to find is that when you divide it, you end up with exactly the same result. So the strain is going to be 0.1, no units to it. Okay, then in part C, what is the elastic moduli for steel? So we know what the stress is, we know what the strain is. So now we need to find the elastic moduli, and so we plug into the formula there, and it turns out to be 2 times 10 to the 11th newtons per meter squared. And here is some typical elastic moduli. So if you want to blow that up so you can see that better, but that shows the range of values for different kinds of materials and what their elastic moduli are. All right, we're going to take a break, and when we come back, we're going to apply these principles to a spring.